right, we're over here in Desmos just to remind you really quickly of what these graphs look like, these exponential functions. Remember that the growth graphs, the ones that were rising from left to right, had big bases, and then the decaying graphs that were sort of falling from left to right were the ones that had the tiny bases. All right, so we want to take this over to a couple of applications. So here I've given you two functions, exponential functions, that are modeling two bacteria cultures. All right, so we have one f of t and g of t, where t is the number of hours since the culture began. So this is very typical for exponential functions to use t instead of x because t is frequently representing time. Okay, so t is in hours in this case. And the reason we were on Desmos, remembering what the shapes of these graphs look like, notice that the bases for both of these functions are bigger than 1.02 and 1.04. And what that means is that just by looking at these functions, we can tell that these bacteria cultures are growing. They're increasing in number because we know that the graph of those functions is going to be rising from left to right. And the first thing I want you to do is just to find f of 0 and g of 0. F of 0, I'm just going to plug into the f of x function, 100 times 1.02 to the 0. Remember your order of operations. We're going to do that exponent first, 1.02 to the 0 is 1, and then we multiply by 100, and we get 100. Same thing for g of t. I'm going to plug in g of 0. That one is 65 with a 1.04 to the 0. And let's see, so we got 65 times 1, and we get 65. All right. So way back in a couple of videos ago, I told you that that number that's out in front of the exponential function is called the initial value. This is why we plugged in t equals 0. This is like 0 hours after I started these bacteria cultures. And because of that property, the base to the 0 is going to be 1. You're always going to get that coefficient of the exponential function as the t equals 0 value. So this is the initial value. When t equals 0, that's right at the moment I started these bacteria cultures. These are the number of bacteria that I have. So we started with 100 bacteria. In the first culture, and the second culture means that we started with 65 bacteria. Second question, which culture is growing faster? To figure this out, let's think about something easy like t equals 3. So if I plug in f of 3, and we get 100 times 1.02 cubed, and then g of 3, 65 times 1.04 cubed. Think about what that means. That means 100 times 1.02 times 1.02 times 1.02. And same thing here, we'll start with a 65 and then we have 3 1.04s. All right, so we've had 3 hours passed. For each hour, we're multiplying by another 1.02 or another 1.04. So f of x, each time I tack on another hour, I'm gonna tack on another 1.02. For g of x, every time I tack on an hour, I'm tacking on another 1.04 multiplier. Okay, so 1.04 isn't that much bigger than 1.02, but it is bigger. So even though we have a smaller number to start out with in g of t, I'm multiplying it by a bigger number for every hour that passes. So we're going to say that because the base is bigger in g of t is growing faster. Third question, which culture has more bacteria after 1 day? All right, so after 1 day, our function is measured in hours, so I need to be careful here that I just need the formula to tell me how many bacteria it has after 1 day. I need to plug in 24 hours. So we're going to find f of 24. And I'm going to find g of 24. And we are definitely well beyond my mental arithmetic capabilities, so let's pull out the calculator. Okay, so let's plug in 100 times 1.02 raised to the 24. And I get 160.8 and change. And let's do the same thing. 65 times 1.04 to the 24. And I get 166.6. All right, so I have more in bacteria culture G. Before I do that, I'm going to change one little thing. Remember what these numbers represent. These are bacteria. You can't have 0.8 of a bacteria. It's either there or it's not. So we're going to round both of these conventionally. 0.8 is going to round up to say that after a day I have 161 bacteria. And then this one is going to round up to 167 bacteria. So after one day, G of T ends up being the one that has more bacteria. And it's because its growth rate was higher. So those 65 bacteria, because they had a faster growth rate, overtook the culture with only 100 bacteria. All right. And it's important to remember that these kinds of equations are only approximating it. It doesn't mean that this culture that's modeled by this at exactly 24 hours is going to have exactly 167 bacteria. It's a model. It's an approximate. It's going to be off by a couple of bacteria here and there. It's the way modeling works. This one asks us, how long until you have 1,000 bacteria? And this is a really important question to talk about. All right, so how long? They're asking you to solve for T. So this time they're not asking us to plug something in for T. How long until you have 1,000 bacteria? They're asking us to plug 1,000 in for the actual function value. So they want to know, when is this function going to spit out 1,000 bacteria? And so I'm going to leave that T as an unknown. And we could do the same thing for G of T. We could start solving this equation by dividing both sides by 100. So that tool we have in our toolbox. And we get a 10 on the left. And then we've got 1.02 to the T. And here's where we get stuck with what we know so far. Normally, the way that we deal with solving equations with exponents is with roots. So like if I had the equation x cubed equals 15, then I would come along and I would use a cube root. I would just match my root to the exponent there. I can't do that here. My exponent is a t. I can't take the tth root of both sides. And it's not 1.02 times t, so I can't divide both sides by 1.02. So the problem is that I need a mathematical tool that we don't have just yet. And this is where logarithms are going to come in. And this is where we're going next time I see you.